second favorite Kiwi in a room with only one Kiwi. I'm not sure how much of a compliment that is, Terry. Thank you. Before I start, I'd like to thank the organisers for giving me this chance to speak. It's been a very nice week. I've really enjoyed the conference. And so, in the last talk, Ting-Hung was basically talking about vertex operator algebras that, depending on how you look at it, are maximally nice. And depending on how you look at it, what I'll be talking about now, this will be vertex operator algebras that are maximally awful. But I would like to argue that actually not really. Things are much better than you might pessimistically assume. So the outline of what I'll talk about is I'll first contrast this maximally nice rational world a little bit with the not so nice logarithmic world. But this will be very short, and most of the talk will be spent talking about a specific example, because I didn't want to assume that people here are all familiar with VOAs, so I'm just going to boil it down to a very easy representative example that exhibits all of the structure I want to be talking about. But this is also a bit of a safari, because in this not so nice logarithmic landscape, we don't really know yet what the right axiomatic approach is, what the right assumptions are. So we're still just going out and exploring and having a look at what happens. So to contrast rational and logarithmic vertex operator algebras, I want to sort of give a very incomplete list of what I sort of associate with the word rational vertex operator algebra. The first is that the module theory is semi-simple. So each module will decompose into a direct sum of simple modules, and in particular, this implies that the Virasoro L0 operator will be diagonalisable, and you can grade these modules by L0 eigenvalues. And rationality also includes there only being a finite number of inequivalent simple modules. And Zhu famously showed if you have semi-simplicity and an extra technical condition called C2 cofiniteness, then the characters of your modules carry an action of the modular group. And this ties in to this whole famous modular tensor category picture, where you can use the modular properties of the characters to compute the fusion of VOA modules. Now I've just quickly sketched what the Verlinder formula looks like in the version that I like it. So you take any two simple modules, Mi, Mj, there's only a finite number of isomorphism classes of these, and everything is semi-simple, so whatever you get you can decompose again into simple modules with some non-negative integer multiplicities. And the Verlinder formula sort of gives you a way to easily compute this. I mean, you can try and compute these things explicitly by really constructing this module and then decomposing it, but that is incredibly painful. And the Verlinder formula then takes one of the two generators of the modular group, and you sort of decompose its action on the level of characters and write it out as a matrix. And so it then relates the coefficients of this matrix, the ratio of the coefficients of this matrix, to exactly these non-negative integers that you get in the composition of fusion products. So that's sort of what I associate with rational VOAs. So what happens when we go beyond rationality, or the obvious jokes of abandoning rationality? And that's the logarithmic setting. So first of all, the important or defining feature is the module theory is not semi-simple. So you'll have modules with proper submodules that have no complement. You won't be able to write them as direct sums. And in particular, this can lead to the L0 operator having Jordan blocks. And it is these Jordan blocks that, when you sort of try and work out correlation functions in the conformal field theory, that will cause logarithmic singularities in your correlation functions, which is where the name logarithmic comes from. So if you look at this slide and sort of wonder, what does this have to do with logarithms? The logarithms come in the correlation functions. But we won't actually be looking at correlation functions today. The vertex operator algebra can still satisfy the C2 condition that was briefly mentioned by Ting-Hung as well, and that would still imply that there's only a finite number of inequivalent simple modules, even in the logarithmic case. But unfortunately, if you do have the C2 cofiniteness condition, then the action of the modular group does not necessarily close on just the characters of your modules. You have to sort of extend what you're working with to so-called torus one-point functions. Or another, perhaps more pedestrian way of saying this is, if you take the modular transformation of some character, you'll get a linear combination of characters, but the coefficients will now depend on the modular parameter. So you get, yes?
What is a torus one-point function?
So that is a correlation function involving only one field, one representation, but instead on the Riemann sphere, it's on the torus. And so it depends on the modular parameter of the torus. And but if you put in nothing, if you just have the vacuum inserted, then it's a character. And if you put in different operators, then it's a more general class of things that you can consider, and those are the torus one-point functions. But this is the only point in the talk where this word will appear. So, and the important statement is you just have to sort of go beyond characters to get a proper action of the modular group. Or if you restrict yourself to characters, then it's not really an action because the matrices that you write down now depend on this torus modular parameter. And so instead of having numbers here, you'd have polynomials, and generally the ratios of these polynomials are not non-negative integers. So there's no obvious way to interpret this as a Valunda formula. And the modular category that you get is not a modular tensor category, because modular tensor categories, among other things, require them to be semi-simple. That's part of the definition. But due to humongous work of Huang, Lipolsky, Zhang, and then various subsets of those names, they have managed to show that you still get a tensor category structure and a braiding, but there's always a problem of ensuring that you've chosen your category to be big enough. So if you're too naive in your definition of your tensor category, you might want to work out the tensor product or something, and it just lies outside of that because you haven't been generous enough in what you're taking your tensor category to be. And the other thing is the Valunda formula in its naivest formulation can't possibly work when your module theory is not semi-simple, because the character of an indecomposable module and the character of the direct sum of the composition factors of the module are the same. And so your characters are just necessarily lossy. You will not be able to reconstruct, you'll not be able to uniquely identify a module just from its character. So at best, the Valunda formula can only tell you fusion at the level of characters, but so the moral I want to sort of present at the end of this talk is that, at least in some cases, this is what you can get. I mean, you can at least get fusion at the level of characters. And so the example I'd like to consider today is one of the sort of easiest examples of a vertex operator algebra, in that it is very easy to define and yet sort of violates almost all assumptions that Cheng Hong had in his talk before. If you're going to write this down from a sort of generators and relations perspective, this vertex operator algebra has two generators. They're normally called beta and gamma, and they satisfy very easy operator product expansions. So the crosswise operator product expansion is non-trivial, and like with like is trivial. And you can choose a conformal structure. That means an energy momentum tensor, and there's an extra distinguished field J, which gives you a nice grading on this vertex operator algebra. And but because I didn't want to assume that people are comfortable with VOAs, we will now just break this down into an exercise in Lie theory and just use the VOA structure to inform us in how we do the Lie theory, but you won't actually need any more VOA theory from now on. And so what these operator product expansions imply is that if we write down these fields is expansions where we have a formal variable and some coefficients, then these coefficients satisfy these commutation relations. And so there is a central element, and while formally at the level of the Lie algebra it is just a central element, if you want to connect this back to VOA theory, this really needs to be identified with the identity operator whenever you're acting on modules, which is why I've just written it as a 1. I feel there's no point in putting some abstract symbol and then re-identifying it with 1 at a later stage. You also see that as long as this thing is non-trivial, by appropriately rescaling your betas and gammas, you can always get it to act as 1.
This is just commutator.
It's just ordinary commutator. Yep. Yeah. So there is a super version of that where here you wouldn't have a minus in front of it, and then you'd have anti-commutators, but that you have commutators. And so vertex operator algebras again sort of suggest a triangular decomposition of your ghost Lie algebra. And I put a prime here because I want to think of this in a way as a derived algebra of one that I'm going to make slightly bigger in a moment. In the way where when you have a loop algebra and its extension, you can then extend it more to add a degree operator. We'll just be adding degree operators in a moment. But these degree operators will essentially be coefficients of these fields. And so we now split this up. We have our central element. We have two zero modes. And then we have modes with either positive index or negative index. We take the stuff with positive indices to be positive roots or annihilation operators. The stuff with negative indices to be negative roots or creation operators. And then the gamma zero mode will also be a negative root, and the beta zero mode will be a positive root. But again, if we want to sort of look at this and do a bit of Lie theory and have root vectors and things like that, it's good there's some kind of grading of this. And here we have nothing that sort of does these gradings, and so we augment by two extra operators, J0 and L0. These are actually the zero modes of these fields, so they're coming from the universal enveloping algebra, but we're just putting them in there. And L0, just with one of these generators, if you take the Lie bracket of L0 with beta or gamma n, then it gives you minus n times the thing that you had. And here it's, yeah. So this is just the way it's normally done in, with a degree operator in affine algebras. And so now the naive module category that we'd like to consider when you're doing Lie theory, category O, is a very popular category to work in. So with the triangular decomposition that we have, we can now create our candidate category O. So we want all ghost algebra modules satisfying, first of all, that the central element really does act as one. We need this for these things to make sense as VOA modules. We'd like it to be finitely generated. For J0 to act semi-simply, we'll take this to mean it's a weight module. Together with finite generation, this then also implies that all weight spaces, if you include the L0 grading, will be finite dimensional. So we have characters and things like that. And we want the action of the positive roots to be locally nilpotent. And what I mean by that is you take an element in the module and you apply the universal enveloping algebra of the positive modes, positive roots, and that should just generate something finite dimensional. This is not the weakest possible assumption to get a VOA module. I mean, we'll be weakening this a little bit in the moment.
But L0 is not acting.
L0 does not need to act semi-simply. This is, since the title contained logarithmic conformal field theory, assuming that L0 will act semi-simply is going to kill out, is going to kick out all the logarithms. So we do not want to assume this. And it's the color. I chose a bad color scheme. So there's supposed to be a gray here that looks exactly like the white, which is a pity. So what you get when you think of this definition, this here implies that any such module M will actually contain a highest weight vector, and actually it contains a highest weight vector on which J0 and L0 act trivially. You just have to work through the algebra. And in the end, it boils down to that this category is semi-simple, and there's only one simple object, V, which is actually the VOA as a vector space. And I've sort of sketched it here. We start with the vacuum vector. We can apply powers of gamma naught or beta to the -1, beta naught annihilated. And if you look at the J0 and L0 grading, the J0 grading goes horizontally. It decreases with gamma, so each extra application of a gamma gives a -1. Each application of a beta gives a +1. And negative modes increase the conformal weight. And you might perhaps be a bit irritated that sort of conformal weight or energy decreases as you go down. But to that I say I'm antipodean, so if you're down in Australia, it's the right way up. And it's also just the way these things are normally done if you say highest weight module. But so this category, okay, it only has one object, and we can sort of have a look at, if we want to do conformal field theory, you have to see if this closes under fusion, and because this is the VOA, i.e. the vacuum module, the fusion of that with itself is always just the vacuum module, so yes, it is closed under fusion. But the action of the modular group does not close on this one character that we have, so it's not a holomorphic VOA. because the central charge is 2, it's not 24. Or
So I'm puzzled. Everything was symmetric in L0 and J0, but now you've got an asymmetry. What does that mean?
this comes from the fact that in our triangle decomposition we put beta naught. In L0 and
There's nothing.
I mean, they're different operators, right? I mean,
You were saying that L0 is not semi-simple in J0.
yes. So here we don't get anything logarithmic. So we have to go to a bigger category before anything like that happens. So yeah, in particular here, L naught is semi-simple.
Question.
Yes.
You have, in any case, you start with a VOA, so the
Yes.
VOA is graded.
The VOA is graded. Yes. I mean, this is the VOA actually as a vector space.
Two fields are dimension 0 and 1, or
The two fields have dimensions 0 and 1. Yes.
and this is gamma 0 dimension.
So gamma 0 is the gamma field, and beta minus 1 on the vacuum is the beta field. Yes. Okay. And you can work out the character reasonably easily if you're familiar with these things. So you take the character as just the trace of some formal variables z and q to the j naught and L naught minus c over 24, and you can just sort of easily sort of count how many betas and gammas you'll have at any one of these points and work out what the character is. And I've written this sort of in a product form, and this is a little bit naughty because this is an analytic continuation of a power series which has annuli of convergence. So you have to remember where the region of convergence is, and this will come up again a little bit later. And so, well, that's not big enough. So let's try and find a way to get new modules. And a nice way to get new Lie algebra modules from modules that you already have is to consider twists by algebra automorphisms. There's two nice algebra automorphisms to consider. One is called conjugation, where you replace the betas by gammas and gammas by minus betas. And then you can work out what this does to the L's and J's. And that's what happens. J goes to 1 minus J, and L naught just stays the way it is. And there's another automorphism which later on will prove to be more interesting, called spectral flow, which shifts the mode indices of the betas in one direction and the mode indices of the gammas in the other direction. And then J naught gets a couple of multiples of the central element added, and L naught gets changed. And because it changes L naught, it's changing the conformal grading, and this is what's called the spectrum often in physics, and so the spectrum flows. That's why this twist is called a spectral flow. And so if we have a module and an automorphism, we can define a twisted module by taking exactly the same vector space and just twisting the action. So it is apply the inverse of the automorphism to the Lie algebra element and action with it. And you can then work out what happens to this one module that we know. And well, since these two automorphisms do not respect the triangular decomposition that we had, I mean, they muck it up, you get a different module. And so you sort of fall outside of that category that we were in before, but you can still have a look at what it looks like. And it turns out that the first inverse spectral flow and conjugation do the same thing to the vacuum module. And so if we look at it, I've now replaced capital omega by little omega. This is the image of that vector. And you now get something where you can have beta naught acting non-trivial and take two arbitrary powers, but now gamma naught truncates, and you can act with the gamma minus ones. And you can now work out the character of this thing. And I'll quickly do that on the board, the way you get this. And so what you do is you use the fact that you know the character for the vacuum module already, and you know what spectral flow twists do to your Lie algebra elements. And so you can start from the character of and I'm now actually doing it the wrong direction. There. So we start from that character, and this was the trace. Like this, but this is just the same as moving the twist up to the algebra generators. and the twist doesn't affect the level. And if you then work out what this is using these spectral flow rules, you'll get that this is in the end, it's just Z times the character of the vacuum module, where now you invert the Z variable. And if you work this out, you will get exactly minus the character that you had for the vacuum. But this is weird, right? I mean, formal power series, they count dimensions of graded spaces, and so if you take minus a formal power series, suddenly your dimension is supposed to be negative. No, of course not. I mean, by doing this transformation, we've actually changed the region in which we're expanding this formal power series, and so we have a different annulus of convergence on which this must be expanded. And so I guess the upshot of this mini exercise is it's convenient to write down characters and product formulae, and so, but we have to really keep in our minds where we're actually expanding these things. I mean, these characters have to be formal power series. They should not be analytic continuations. And so, but now this picture of the module sort of suggests to us maybe how we would like to generalize our category. We don't necessarily want beta naught to annihilate everything. We want to allow beta naught to act freely, not just gamma naught to act freely. So how do we enlarge our category? Well, we go from a triangular decomposition to a parabolic one. We now sort of take our annihilation operators to just be the betas and gammas with positive modes, and the creation operators to be the beta and gammas with negative modes, and everything with a zero mode just sort of act. And now we can try and induce from representations from modules of the zero part and get bigger things. Or if you want to write this down as a definition for an appropriate module category, we now take the category of B modules M satisfying 1 has to again act as the identity operator. We want it to be finitely generated again. We still want weight modules, so J naught to act semi-simply, but now we only demand that this smaller algebra act locally nilpotently.
How was it bigger before?
So before it was smaller. We're now enlarging it. So this beta naught used to be part of that.
It used to be part of that.
Yep. But we now no longer require beta naught to be an annihilation operator.
And gamma naught was part of the other.
Yeah, gamma naught was part of the creation operators. And within a module like this, you can always show that there is a vector, if you go sufficiently down, that will be annihilated by this stuff. And so you can now look at vectors that are annihilated by this, but they'll still sort of span some module by the action of this algebra. And so you can, the simple objects in this category can be induced from simple modules over the algebra. And so we can have a look at what we get. And well, this algebra here is just the Weil algebra, and Bloch classified the simple modules for the Weil algebra. And they basically fall into three cases. One is we have a highest weight module, which is basically just the top of this module. The other case is we have a lowest weight module, which is the top that we have here. That's these two first cases. And the last case is we have a so-called dense module where we have some vector u lambda, and now we just allow beta naught and gamma naught to act freely on that, and that sort of traces out a dense module, and its weight support will just be the integers shifted by whatever this weight lambda is. And so we also have a periodicity, so if we have two of these dense modules whose weights differ by an integer, then they're actually the same module. And we can also sort of pack these two modules into one that looks a bit like one of these, and I'll just be calling them W0 plus and minus, because there's two different ways you can put them in there, and they're characterized by these two non-split exact sequences. So this is now this larger category R that we can look for modules in and try and do conformal field theory in. And we can now induce from these modules. So V and V star, the highest and lowest weight modules, were just the vacuum and the conjugate of the vacuum, or the -1 spectral flow twist of the vacuum. And we denote the inductions of these dense modules by just dropping the bar over the top of them. And you can then work out, it's not too hard because the Lie algebra is so easy that these are exactly the simple objects in category R. But now you might say, okay, we still had this spectral flow twist. What does that do? And that again takes you outside of category R. I'll be showing a picture in a moment that will sort of illustrate that. So non-trivial powers of the spectral flow twist of these dense modules will take you out. And you'll see in a moment why. And so now we need to do one last, hopefully last, enlargement of the module category. And here I'm actually appealing for help. I'd like a nice way to characterize this category. So the best we have so far is you just take the category of ghost modules generated by V and these dense modules W and their spectral flow twists, and then you also allow for extensions. And when you do these extensions, that's where you get non-diagonalisable action of L0, and you'll see an example of that later on. But this is a rather clumsy way of trying to define that representation category. And so,
Including twisted modules in this category.
sorry?
You are including twisted modules.
I'm including twisted modules, and I'm
in the definition of the category.
yes, and I'm including extension between different twists.
But not all of them, just certain twisted modules.
Just sorry, the twists by these two automorphisms, the C and the sigma, spectral flow and conjugation.
And you made lambda real for some reason.
Yes, that's to get nice modular properties later on. I'm restricting to real lambda. You'll see later on in the modular transformation formula of the characters that restricting to the reals is a good idea. And so I just wanted to sketch what these modules look like. You could probably already imagine it. You have your one weight vector that you act on freely with the betas and gammas, and that sort of spans out an infinite dimensional space at the top. Each one of these points is just a one-dimensional weight space, but then the dimensions go up as you go down. And you can work out the character of this thing. And I forgot to write here, again, you have to assume that Q modulus is less than 1. And for the Zs, you have, it doesn't converge anywhere. This is an algebraic delta function in the Zs. And so we sort of completely abandon having product formulae or anything for these things. In fact, if we went here to W0, that was where we had these non-split exact sequences after you induce. You see that the character of one of these is equal to the character of this plus the character of this. And we had here that the two characters are their opposites. So if you were to work with analytic continuations, then the characters of these W's would just be 0, which really tells you, I mean, delta functions in many ways look like 0 if you just go in a random spot and you're not at the point where they're supported. So that kind of motivates that. Okay, so what do the spectral flow twists look like? So if you look at the spectral flow formulae, I mentioned before, they change L0, and so they affect the L0 grading. And so I've just drawn it, sort of what this looks like. If you take the L0 grading to be the vertical direction, they stay the same as vector spaces, but you're just tilting what your L0 grading is in the direction. So I always say the L0 gradient increases as you go down. And so what happens is at the beginning, so the stuff that was in category R had bounded conformal weights, but as you twist further, you get stuff where the conformal weights are not bounded. So this line just extends infinitely far. But if you're in any particular sort of vertical line, this is the lines of constant J0 eigenvalue, within that you'll have a bounded conformal weight, but there's just no global bound. And you can do the same with the W's, and you can just keep, the more you flow, just the steeper this line gets. And so, again, from sort of a rational VOA perspective, this is horrible, but this is sort of what we get. This seems to be the category we need to work in. And the action of the modular group actually closes on the span of the characters of these modules, if you include spectral flow twists. And so it closes on just the W's. If we include, I should have included 0 in this interval. So we had these things with these non-split exact sequences, but I mean the characters of W plus and W minus are the same because the composition factors are the same. So at the level of characters, we don't need to distinguish those. And so you can work out the modular transformation of these characters, and you get, well, we now have a continuous parameter, so we have to, instead of sums, we get integrals. But you see that these coefficients, these are just Fourier transforms. And the reason why I've now restricted myself to real weights is because these integrals are always over real weights, and so you want closure.
These characters are just formal characters, right?
They're just formal.
So how does the modular group act on formal characters?
Well, I mean, you literally do the modular group transposition. I mean, basically, it's the same as when you do the modular transformations of the characters of Fock spaces or whatever. You get these, you just plug it in and work it out. I mean, it's, I guess I'm not quite sure what you mean. You just, I mean, it's always done in terms of these integrals. I mean, you just have to work out these integrals, and so, yeah. And what you get when you look at this basis, you see that, well, it's also if you swap the two sides of this coefficient, it's symmetric, and if you sort of swap it and conjugate it, and then multiply these two things together, you get actually an identity operator. So this matrix, this S matrix is symmetric and unitary in this basis, so it behaves a lot like the way you'd like S matrices to behave in rational cases. And you might also ask, I've just written down S transformations for these W's, but not for the vacuum. And for the Verlinder formula, we need S transformations of the vacuum, so we need to be able to work that out as well. And here we use the fact that we have these non-split exact sequences that we can splice to get resolutions of the vacuum, and then you can use the Euler-Poincare principle to express characters of the vacuum in terms of these W characters. And so you can then, again, this is all formal, you plug the modular transformations of the W characters in, and you can then work out what the modular transformation of the vacuum is expanded in terms of W characters. And you get this coefficient. And so now, because it was the first slide, I'll just recall the rational Verlinder formula again, so we can now contrast the proposals in the logarithmic case. And so again, we had a finite number of modules mi, and we decomposed the fusion product into mk's, and we have these non-negative integers, which are their multiplicities. And the Verlinder formula says that these multiplicities are just this ratio of S matrix coefficients, where the denominator uses the vacuum row or column of the S matrix. And so, well, we have now these W's, which sort of form our basis. And we have vacuum transformations. So we now have an obvious generalization of what this new Verlinder formula should be, at least at the level of characters. So we now take some two modules, M and M, and their fusion product. Well, we want to think of it as something, because there's infinitely many of the doubles, we'll now have to write it as some integral over all of them with some multiplicity. And of course, you'd have to hope that in the end, after you perform this sum and integral, that you only get a finite number of modules. And we'll see later on that that's what you get. I mean, essentially these multiplicities will be non-negative integer multiples of just delta functions. And so the obvious generalization of the Verlinder formula is now, again, that you write this quotient of S matrices, where in the denominator you have the vacuum S matrix coefficient, and then you always have M translating, so M to the reference, N to the reference, and then the stuff that was that you were fusing to the reference with complex conjugate. So this is exactly just this formula now, assuming that this index is somehow continuous and still just a finite index.
So this may be the same as theory space, but how do you define this fusion?
So this is right now is just exploring the modular properties. We then afterwards did spot checks where we really did fusion using the Nahm-Gabadil-Kausch style constructions, where you really write down the vector space as a tensor product, and then you have certain identities you have to impose to take quotients and try and really work it out. And we did spot checks, and it turns out in spot checks it matches what this formula predicts. But this is, yeah, as I said, this is still exploratory. I mean, we can't prove yet that this really is the Verlinder formula.
Even in the rational case, the fusion is quite a subtle thing. Right?
It's a very painful thing to have to really work out by hand.
Do you have some kind of abstract definition of fusion, or you just...
We have nothing beyond Huang-Lepowski-Zhang, which is not that constructive. And so we don't have a satisfying definition of fusion. But what you can, so you can now just posit this product, and what you can see is that when you, so the conjugation of both factors is the same as first fusing and then conjugating. Just everything's at the level of characters, that's on this product. If you spectrally flow both factors, then it's the same as the sort of the sum of both spectral flows applied to the product. Again, this is always done at the level of the characters with this Verlinde product. And then it also shows you that the vacuum fuse to the vacuum gives the vacuum, which is certainly what you'd want for an actual fusion product. If you gave something else, it would be terrible. The vacuum with these W modules are the W modules, and the product of two W modules gives you a sum of two W modules, one of them spectrally flowed.
So these characters, these formal characters are clearly linearly independent?
Yes, they're linearly independent. Sorry, I should have said that. Yes. They're linearly independent just because you have this, as long, yeah, you're just restricting this to one, so the leading power is just different. And so, well, you get this prediction of a Verlinde product, and now in certain tedious spot checks we can work it out, and we've done quite a few, and in all the cases that we checked it, it worked. And at least, so if you were to believe this formula, the right-hand sides here, in many cases these directly characterize what the module would have to be, unless the arguments of these W's happen to be 0, because then already we know we have these non-split exact sequences, so it's not sure if it's the W plus or the W minus. And so it is now interesting to try and work out what do you get here in the case when the weights do add up to 0, or add up to an integer. And so we did this, and that is quite a painful calculation, which I'll just present the result. And what you get is a big module that has, as a submodule, it has the vacuum. So I'm presenting the spectral flow inverse of it, because it has the nicest presentation. You get the submodule as the vacuum. If you quotient by that, you have a direct sum of two simple modules sitting inside that. So once the spectral flow inverse of V and the spectral flow of V, once you quotient those out, you're left with just the vacuum. Or you could write this as being either of these two non-split exact sequences. And so if you compare this back again with the character thing, you get a W plus the spectral flow inverse of a W. And so if you adjust that appropriately, that's exactly the character that you get. So that works. And so this thing now really has L0 Jordan blocks. So you have what corresponded to the vacuum vector of the VOA sitting in here, and in here, and L0 on the vacuum vector up here sends you down to the vacuum vector down here. So this really is logarithmic. So the beta gamma ghosts, which are sort of one of the fundamental building blocks of VOAs or CFTs that have been here since the early days, actually they have logarithmic behavior if you look at the right representation category. And so what we believe, but at the moment do not have the tools to check, is first of all that these W's, as long as lambda is not an integer, are simple, and in this category T admit no extensions. I should probably have said not just protective but also injective, so they shouldn't be able to show up as non-trivial submodules or quotients of anything. We also believe that these P's are projective, and it would be nice to think that this Verlinde product actually matches the real fusion product, which it does in spot checks, so there's a good reason to believe that this is the case. And so this program that I've showed you, we've done this a number of times, and the general pattern that has emerged so far, I mean it's all been exploratory, is that there is a sort of preferred class of modules which we've called standard modules, which are these W's, and they're parameterized by some space M, and you have some measure on this. So if this were rational, then M would just be some finite set, and you have the counting measure. Here we had M was a Cartesian product of the interval 0 to 1 and the integers. So we had all the W's and their spectral flow twists. The subset of M corresponding to standard modules where you have indecomposability going on is restricted to a subset of measure 0. So this was just at parameter equals 0 or 1 or integers. And the simple standard modules, we believe, hope, admit no extensions. And the characters of these standard modules form just a formal basis of the span of all characters, so they're linearly independent, and you get action of the modular group on this span of characters. And the S matrix that you get is symmetric, unitary, as in, you know, swap the indices and conjugate it and then take its product with itself, you get the identity operator. And the square of the S matrix turns out to be conjugation, which was the conjugation twist orthomorphism which we had in the thing. And then so writing down the obvious generalization of the Linde formula leads to something that looks like what you'd hope the fusion product to be. And so the algebras that we've done this for are the free boson, though this might have just been done in notes. I couldn't find the reference for the free boson for some reason. But the other cases include the 1p and pq singlet algebras, which are infinite order orbifolds of triplet algebras, which were the first ones where logarithmic behavior was really studied. The beta gamma ghost system, which I showed today. Affine SL2 at admissible levels, so these are certain fractional levels, but they're non-integral. And also, just recently, affine OSP at one of the admissible levels, and it should be true at all of them, but we haven't finished the module classification in this category R to be able to even determine characters and check this. And there are more examples. I didn't want to make the list too long. So this looks convincing. It's one way of, I guess, saying that this logarithmic stuff does have nice structure and it's not as awful as you might think. You might also ask why we're looking at these examples where there are infinitely many modules. We could have gone to this place where you had the C2 cofiniteness condition, where you only have a finite number of inequivalent simple modules. And Terry has some very interesting work on that, and certainly stuff that I'm also considering. And Terry's proposal is very interesting, but they say that one of their main obstacles is that there's not many examples to really test it with. And essentially what you can see from this list is everything here is some variation of SL2 or rank 1 stuff, and everything is so far stuck in rank 1. And so my current work is to try to escape rank 1. So we're now starting to do SL3 and rank 2 things. And the thing that sort of goes wrong when you have this C2 cofinite thing and only a finite number of modules, finite number of inequivalent modules, is the non-semi-simple stuff, which kind of mucks up your modular properties. When you only have finitely many modules and finitely many of them are bad, then this is not a set of measure 0 that you can just sort of ignore and integrate out, and you have to deal with it on the face. And Terry has come up with some interesting ways of dealing with it, but this is another approach that sort of just pushes the problem under the carpet and also seems to work nicely. And so that concludes my talk.
Any questions?
Yes.
No, it was one.
Okay.
Okay, so maybe I got this wrong, but I thought there was a claim that if you take the k goes to infinity limit of the minimal, just the ordinary minimal rational CFTs, it's certainly irrational, but I think a logarithmic CFT, I think there's a claim. But then this seems like it would be,
So the k goes to infinity, so the central charge goes to infinity?
No, the central charge goes to 1.
Goes to 1, yes.
So this is just the ordinary SU2 level k coset minimal.
Yep.
SU2 cross SU2 mod SU2 minimal model.
Mm-hmm.
You take the k goes to infinity limit.
Yep.
I believe that, well, certainly it's an irrational conformal field theory.
Yes.
The primary goes to infinity, but I believe the claim is that it's logarithmic. I'm trying to,
Yes, because being logarithmic is essentially guaranteed if it's not rational.
Okay. Yeah, right, exactly.
You'll always find, I mean, that's, I think, Hubert mentioned it. I mean, once you go beyond rationality, once your VOA, basically what this is governed with is, does your VOA have, so if you define it universally, so with just, like the elementary, does it have any ideals, any extra normal ordering relations that you can impose, which is what you have in the minimal models. And when you do that, this cuts out all of the nasty representation theory. When you don't, you basically have anything that's a Virasoro module, as long as the fields, when you evaluate them, have some finite pole instead of essential singularities, which is a huge class of modules. And this always admits stuff with non-diagonalisable L0. And so.
Yeah, so the reason I brought this up was just to say that, well, since you have everything's rational there and you can write down all the formulas, is there a way of might there be a way of taking the limit of the rational formulas and then getting your integral? Essentially, discretize. This would be discretizing your integral and things like this in your Berlin formula.
That's an interesting idea. I haven't considered that. I will consider that. Thank you.
So my question was sort of the physics. If I understood correctly, someone said before that these logarithmic things should crop up when you say take a statistical mechanical model where the corresponding field theory is not unitary.
Yes.
Right? So what kind of statistical mechanical model should be giving rise to these things?
So for the beta gamma ghosts, I don't know. I wasn't trying to get them from, I was just trying to find the easiest possible example that exhibit to the pattern that you have. One statistical field theory where you do get these kind of questions is the Ising model has a logarithmic extension, where you now just sort of ask if your islands of one orientation of the spin sort of propagate across the entire system or not. So when you allow for operators that measure these things, then you get a logarithmic.
Would it be one of these ones that you're?
That would be, yes, that's sort of a sub-theory within one of these.
And what would be you would presumably get critical exponents or something for that from the conformal?
You can, but again, I mean, the modules that you, so we haven't yet, it's not yet quite clear how you then go from just the chiral theory to, the full theory. That's still ongoing work. But I mean, in terms of critical exponents from the chiral thing, well, any Verma module of the Virasoro algebra is a module over the VOA that you get from this logarithmic thing. So your critical exponents are everything. Right? Yes?
So I heard somebody told me that for the case of percolation,
Yes.
the continuum limit is going to be C equal to 0 logarithmic.
Yes.
Is this in your list? Or
Yes, that would be P equals 2 and Q equals 3. Though again, I mean, percolation, the actual statistical module is the full CFT, and it's not yet clear how to go from the VOA rep theory to really glue this together to get the honest statistical
I
theory.
suppose you can get some information about the critical exponents from this.
Yes, and so I guess that ties back to the critical exponents you asked there. So there are sort of, I wrote down here the singlet algebras, but when you take the triplet algebras, these are C2 cofinite. And for these C2 cofinite ones, this is work of myself and others, the classification of simple modules has been done, and you can work out the critical exponents that basically the conformal weights that you'd expect from those. And so those seem to be preferred critical exponents that you get in percolation or something like that. But in percolation, it's not clear that you have these extended algebras. You know you have the Virasoro algebra, but you don't know if you have these other extra fields that you have in these singlet and triplet algebras. And so it's not clear if you should be considering these large VOAs that, luckily, they're nice because they cut down the symmetry. Well, they cut down the modules, they increase the symmetry. But it's not clear if that's really what critical percolation is.
Any other questions?
Question on language. So because I'm a little bit confused from this logarithmic, say sometimes non-unitary, sometimes non-rational.
Mm-hmm.
If I correctly understood, it's non-rational. So
It's also non-unitary.
a concrete question: if I take Virasoro with C equal to 1,
Yes.
you call it logarithmic or not?
Again, I'd say this is down to the module category that you choose. So, I mean,
Okay.
I mean, if you choose your module category in such a way that you include modules that are indecomposable, then I would call it logarithmic.
Okay.
But if, you know,
Take only finite direct sum or
Yeah.
simple mode. Okay.
then yeah, but it's not clear. But these choices of representation category, it's not clear how natural these are at the moment. This is still part of trying to find the physical representation category, and so
Get something like direct integral. We say,
Yeah.
of modules, then you get something which is indecomposable
Yeah.
from the algebraic point of view.
exactly,
So it is.
it is, I would say it's logarithmic.
Any other questions? Then let's thank Simon again.